50-foot logs weighing 2 tons, moving at 30 miles per hour down a mountain through a wooden channel, no engines, no horses, no machinery, just water, just gravity, just physics. The log flumes of the American West were engineering marvels that use the simplest possible solution. Let nature do the work. Water flows downhill. Logs float. Combine them correctly, and you can move millions of board feet of timber from mountain forests to valley mills for pennies. The physics are elegant. The execution is brilliant. This is how it actually worked. How gravity and water moved entire forests. How America transported impossible loads using nothing but natural forces. The log flume was physics made practical, engineering made simple, problem-solving at its finest. 1859, Lake Tahoe, Nevada Territory. The Comstock Lode silver mines need timber. Millions of board feet. For mine shafts, for support beams, for buildings, for fuel. The forests around Lake Tahoe have the timber. Old-growth pine, fir, cedar, perfect quality, perfect quantity. But there's a problem. The timber is on the mountain. The mines are in the valley. The distance is 15 miles. The elevation drop is 1,400 feet. Transporting logs by wagon requires teams of horses or oxen, pulling heavy loads uphill, then controlling them downhill. The cost is prohibitive, maybe $15 per 1,000 board feet. That's $480 modern. The timber delivered to the mines would cost more than buying timber shipped from the coast. Makes no economic sense. The forests sit unused. Valuable but inaccessible. Then J.W. Haynes has an idea. A revolutionary idea that will change Western logging forever. Haynes understands physics, understands water, understands that water always flows downhill, always seeks the lowest level, always follows the path of least resistance. He also understands that logs float, have natural buoyancy, will ride on top of water if given the chance. Combine these two facts correctly, and you have a transportation system. No animals needed, no engines needed. Just build a channel. Fill it with water. Let gravity do the work. The concept is simple, almost obvious once you think about it. But nobody had thought about it. Not at this scale. Not for commercial logging. Haynes designs the first log flume, a V-shaped wooden trough, built following the natural contour of the mountain, sloping downward continuously. Water flows into the top, logs get placed in the water, gravity pulls them down. They arrive at the bottom. Simple, elegant, brilliant. The V-shape is critical. This is the first key piece of physics. Why V-shaped instead of square, or rectangular, or round? The answer is self-clearing. A V-shaped channel has unique properties. When a log gets stuck, the water level rises behind it. The rising water lifts the log, floats it higher. The V-shape means the higher the log rises, the wider the channel becomes. More space opens up. The log floats up into the wider section, gets unstuck, flows forward, the jam clears itself automatically. No human intervention needed. Now try the same thing with a square channel. Log gets stuck, water rises behind it. But the width doesn't change. The log stays stuck, the water keeps rising. Eventually overflows the sides. The jam doesn't clear, requires human workers to reach the jam. Remove the stuck log. Break up the blockage, constantly, every single jam. With a V-shape, most jams clear themselves. The geometry does the work. This is elegant physics, using shape to create self-correcting behavior. The V-angle matters. Too wide and logs don't float properly. They sit on the bottom. Drag. Slow down. Create friction. Too narrow and logs get wedged. Stuck tight. Won't clear. Haynes determines the optimal angle through experimentation. Trial and error. Testing different configurations. The sweet spot is approximately 90 degrees, a right angle V. This provides enough width at the top for logs to move freely, enough narrowness at the bottom to keep logs centered, enough self-clearing action when jams form. The 90-degree V becomes standard. Every successful flume uses it. Some minor variations, 85 degrees, 95 degrees, but all close to 90. The physics demands it. Deviate too far and the system fails. The dimensions are specific. Haynes' first flume is 18 inches wide at the bottom, the narrowest point, where the two sides of the V meet, 36 inches wide at the top, where the sides end. The boards are 16 inches wide, overlap to create the V. The depth is about 18 inches from bottom to top of the sides. These dimensions are carefully calculated. Too small and large logs won't fit. Too large and you waste lumber building it. Need more water to fill it. Increase cost unnecessarily. The 18-inch bottom width handles logs up to 12 inches in diameter. The 36-inch top width handles logs 16 to 18 inches in diameter. The 18-inch depth provides enough water volume, enough buoyancy, enough flow. These dimensions prove optimal. Later flumes use similar sizes. Some go slightly larger, 24 inches at bottom, 48 at top, for bigger logs, but the proportions stay similar. The physics scales consistently. Water is the second critical element. Not just any water, flowing water, moving water, water with velocity. Stagnant water won't work. The logs need current, need momentum, need push. The water must flow continuously, fast enough to carry logs. Not so fast it damages them. The optimal flow rate depends on slope. On steep sections, less water needed. Gravity does most of the work. On gentle slopes, more water needed. Must maintain momentum. Prevent logs from settling. From stopping. Haynes designs feeder systems. Small channels branching off streams, creeks, springs. These feeders divert water into the flume. Top it up. Maintain volume. On long flumes, feeders appear every few miles. Keep the water flowing, keep the logs moving. Without continuous water supply, the system fails. The water is the engine, the power source. Everything depends on it. The mathematics of water flow are precise. Water flowing in an open channel follows specific equations. The Manning equation, the Shazy formula. These relate flow rate to channel slope, roughness, and cross-sectional area. For a V-shaped flume with an 18-inch bottom width, 90-degree angle, and average slope of 2%, meaning 2-foot drop per 100 feet of length, the water flows at approximately 3 to 5 feet per second. That's the velocity of the water itself. The logs move slightly slower, maybe 2 to 4 feet per second on gentle slopes, 6 to 10 feet per second on moderate slopes, 15 to 25 feet per second on steep slopes, 40 to 50 feet per second on the steepest sections. That's 30 to 35 miles per hour, faster than most vehicles in 1859. Logs traveling downhill at highway speeds, carried by nothing but water and gravity. If you're the kind of person who believes these stories deserve to be remembered, hit subscribe. The engineers who designed log flumes used pure physics. No computers, no calculators, just observation and mathematics. They figured out fluid dynamics through trial and error, created systems that moved millions of tons of timber. Subscribe if you think elegant engineering deserves recognition. The construction follows the terrain. This is the third key element. The flume doesn't fight geography. It follows it, uses natural contours, wraps around hillsides, crosses valleys on trestles, descends through canyons, goes wherever gravity and slope allow. The route is surveyed carefully. Engineers walk the entire path, mark the line, calculate the grade. Grade is critical. Too steep and logs accelerate uncontrollably, smash into turns, break apart, destroy the flume. Too gentle and logs slow down. Stop moving. Jam. The optimal grade varies. On straight sections, 2 to 4% works well. That's 2 to 4 feet of drop per 100 feet of length. Logs maintain steady speed. On curved sections, grade must be gentler, 1 to 2%. Allows logs to navigate turns safely. On specifically designed steep sections, drop chutes, grade can exceed 20%. Logs accelerate rapidly, exit at high speed. These sections are built with extra reinforcement. Heavier timbers, stronger construction. Designed for the forces, the boards are carefully selected. Clear pine or fir, No knots, no weak spots. Boards are sawn to specific dimensions. 16 feet long, 24 inches wide, 1.5 inches thick. These dimensions aren't arbitrary, they're optimized. 16 feet is long enough to span multiple supports, short enough to handle during construction. 24 inches is wide enough to form the flume sides with minimal overlap, narrow enough to mill efficiently. 1.5 inches is thick enough for strength, thin enough to not waste wood. The boards are placed in overlapping V formation. Each board on one side overlaps its partner on the other side. Creates the V shape. The overlap is sealed with oakum. Tarred rope fibers. Makes joints watertight. Any leak wastes water. Reduces flow. Decreases efficiency. Watertight construction is essential. Workers inspect constantly, find leaks, seal them, maintain integrity. The supports are equally important. The flume can't just rest on the ground, it must be elevated, kept level side to side even while descending front to back. The supports are called trestles or bents. Wooden frameworks, 4 vertical posts, cross beams connecting them. The flume sits on top. The trestles are spaced every 16 feet, every 32 feet on straight sections with gentle grades. The spacing depends on the terrain and the loads. On steep hillsides, trestles might be only 8 feet apart. Closer spacing handles greater forces. On level ground, spacing can extend to 30 feet or more. The trestles vary in height. 6 inches where the flume crosses high ground, 300 feet where it spans deep canyons. The tallest trestles are engineering achievements themselves, massive wooden frameworks, hundreds of thousands of board feet of timber, requiring weeks to construct, skilled crews, precise measurements. Any error in a 300-foot trestle means the flume doesn't align properly. Logs can't pass. The entire system fails. Physics governs everything. Force equals mass times acceleration. F equals ma. A 2,000-pound log accelerating down a 3% grade experiences specific forces. The component of gravitational force pulling it downhill equals the log's weight times the sine of the slope angle. For a 3% grade, 1.7 degrees, that's about 60 pounds of force. Doesn't sound like much, but that force acts continuously, constantly accelerating the log. On a 1-mile flume with 3% average grade, a log starting from rest, 0 velocity, would theoretically accelerate to 89 feet per second. That's 60 miles per hour, without friction, without water resistance. In reality, friction and resistance limit speed. The log reaches terminal velocity, the point where drag forces equal gravitational force. No more acceleration, steady speed. On typical flumes, terminal velocity on steep sections is 30 to 40 miles per hour, fast but controllable. The water provides buffering, absorbs energy, prevents uncontrolled acceleration. Turns are the biggest challenge. Logs traveling straight want to keep traveling straight. Newton's first law. An object in motion stays in motion in a straight line unless acted upon by an external force. When the flume turns, it tries to force the log to turn, but the log resists, inertia. It wants to continue straight, hits the outer wall of the turn, can break through, can break apart, can jam. The solution is physics, bank the turns, just like a highway curve. The outer wall is built higher than the inner wall, creates an incline. The log traveling around the curve experiences centripetal acceleration, pushes outward, but the banked turn redirects that force. The normal force from the banked wall has a component pointing toward the center of the curve, keeps the log moving in the arc, prevents it from breaking through. The banking angle must be calculated. Too little and logs still hit the outer wall. Too much and logs slide down toward the inner wall. Cross over each other, jam. The optimal banking angle depends on velocity and radius. These men didn't have YouTube channels. They didn't have anyone telling their story. Yes, we're changing that. The flume engineers solved complex physics problems with pencil and paper, trial and error, direct observation. They created transportation systems that functioned perfectly for decades. Subscribe if you think brilliant problem solving deserves recognition. The formula for banking angle is tangent of angle equals velocity squared divided by radius times gravitational acceleration. For a log moving at 30 feet per second through a turn with 100-foot radius, the optimal banking angle is approximately 15 degrees. The outer wall should be 15 degrees higher than horizontal. This angle perfectly balances the forces. The log follows the curve smoothly. No impact, no damage. The flume builders learn these relationships empirically. They don't use formal equations, but they understand the principle. They build test sections, try different angles, observe what works, adjust, perfect. The result is optimal banking, calculated through experimentation rather than mathematics, but correct nonetheless. This is practical physics, engineering through observation. The water depth is precisely controlled. Too shallow and logs drag on the bottom. Excessive friction, slow movement, risk of jamming. Too deep and you waste water. Need more volume, more feeder systems, higher cost. The optimal depth keeps logs barely floating, just enough buoyancy to lift them clear of the bottom. The bottom of the V is 18 inches wide. A log 12 inches in diameter sits in this V. Partially submerged. The water depth, measured at the deepest point in the center, needs to be about 8 to 10 inches. This depth provides sufficient buoyancy. Lifts the log, but doesn't waste water. The log floats with its top 2 to 4 inches above the water surface, its bottom 4 to 6 inches below the surface. This is the Goldilocks zone. Not too much water, not too little, just right. Flow rate must be sufficient to maintain this depth continuously. As logs pass through, they displace water, create waves, turbulence. The flow must compensate, replenish, keep depth constant. The logs themselves contribute to the physics. Their shape matters. Their weight distribution matters. A round log 12 inches in diameter and 50 feet long weighs approximately 2,000 pounds. That's if it's freshly cut. Green, full of moisture. The weight creates inertia, resistance to changes in motion. A 2,000-pound log traveling at 20 miles per hour has significant momentum. Momentum equals mass times velocity. That log has momentum of about 58,000 pound-feet per second. To stop it requires applying force over time, or distance. Without braking systems, the log must decelerate gradually. The water provides deceleration, drag forces, turbulent resistance. On flat sections, at the end of the flume, the flow slows. The grade levels out. Logs decelerate naturally. Come to rest, ready for retrieval. Friction is both friend and enemy. Too much friction slows logs unnecessarily. Wastes energy, requires more water volume, more flow rate. To combat friction, some flume sections are greased, literally. Animal fat, tallow, applied to the bottom and sides of the V, reduces coefficient of friction. Logs slide more easily, move faster with less water. On steep drop chutes especially, grease is essential. Without it, logs would slow down, might stop, cause jams. With grease, they accelerate smoothly, reach terminal velocity, exit at design speeds. The grease must be reapplied regularly. It washes away, degrades, loses effectiveness. Maintenance crews walk the flumes, carry buckets of tallow, coat the sections, keep everything slippery. It's constant work, essential work. Without it, the physics don't work optimally. Buoyancy follows Archimedes' principle. A log displaces water equal to its submerged volume. The displaced water's weight creates an upward buoyant force. If the log weighs 2,000 pounds and its submerged portion displaces water weighing 2,000 pounds, the log floats at equilibrium. Neutral buoyancy. Most logs are less dense than water. Wood densities range from 20 to 50 pounds per cubic foot depending on species. Water is 62.4 pounds per cubic foot. Pine is about 30 pounds per cubic foot, much less than water. Pine logs naturally float, have positive buoyancy. The log rises in the water until the weight of displaced water equals the log's weight. This happens with about half the log's volume submerged. This is why the 8 to 10 inch water depth works. It submerges roughly half the log's diameter, achieves equilibrium, the log floats, moves with the water, rides the current downhill. If you want to go deeper into these stories, if you want early access to videos before anyone else sees them, join the membership. It's for people who don't just watch history, they carry it forward. The physics of log flumes represent elegant solutions to impossible problems, moving massive loads without engines, without fuel. Join the membership if you want to help us preserve these engineering achievements. The longest flume was 62 miles, the Kings River Lumber Company flume, built 1890, from the Kings River in the Sierra Nevada to Sanger, California, 62 miles, continuous downhill, following terrain, crossing canyons, descending mountains. The elevation drop was 4,200 feet, from 6,500 feet above sea level to 2,300 feet. The average grade was 1.3%, 67 feet of drop per mile. Gentle enough for logs to navigate safely, steep enough to maintain flow. The physics scale perfectly over this distance. A log entering at the top travels approximately 6 hours to reach the bottom. 62 miles in 6 hours. Average speed, 10 miles per hour, maintained by water and gravity alone, no external power. The water flow rate was carefully controlled. Multiple feeder streams added water at intervals. Maintained depth, maintained velocity. The system moved 500,000 board feet daily during peak operation. That's roughly 2,500 logs per day, 40 logs per hour, every hour, all day, all season, for 30 years. The physics never failed. The system worked exactly as designed. The engineering achievement is staggering when examined in detail. 62 miles of continuous V-shaped channel, built through wilderness, through forests, along mountainsides, across canyons. Every section precisely aligned, grade calculated, slope maintained. The survey work alone took 6 months, teams of engineers walking the entire route, measuring elevations, calculating grades, marking the path, finding the optimal line, balancing minimum distance against maximum simplicity. Shorter routes cross more difficult terrain, require more bridges, more trestles, more complex construction. Longer routes follow easier terrain, require less infrastructure. The final route balanced these factors, optimized for construction cost and operational efficiency. The result, 62 miles requiring 13 months to build. July, WR 1889 to late 1890. 400 workers, Chinese laborers mostly, experienced, skilled, paid less than white workers despite equal ability. They built this system, carried materials into remote locations, constructed trestles from canyon floors up, built the V-shaped channel section by section, connected everything, made it watertight, made it functional. The trestles represent engineering marvels themselves. Some span canyons 300 feet deep. The structure is entirely wood, no steel, no concrete, just timber. Vertical posts, 4 feet square at the base, tapering to 2 feet at the top. Cross-braced with diagonal supports, additional horizontal bracing every 20 feet of height. The bottom posts are 40 feet long. Timbers that size are rare, must be specially selected, cut carefully, transported with difficulty, set into solid rock, anchored with massive bolts. Each trestle requires thousands of board feet of lumber. The 300-foot trestles use 50,000 board feet each. The flume crosses a dozen such canyons. That's 600,000 board feet just for major trestles. Then hundreds of smaller trestles, each using 5 to 20,000 board feet. The total lumber in trestles exceeds 3 million board feet. An entire forest used to build infrastructure to move another forest. The irony is obvious but necessary. Without the flume, the timber can't be moved, can't be sold, has no value. The investment in trestles enables moving hundreds of millions of board feet over the system's lifetime, returns thousands of % on the investment. The water management is sophisticated. 7 major feeder points along the 62 miles, each fed by a creek or spring. The feeders are small flumes themselves, 6 to 12 inches wide, running from the water source to the main flume. Distance varies, 50 feet, 500 feet, half a mile. Whatever is necessary. Each feeder has a gate, controllable, adjustable. Operators monitor water levels in the main flume. should open or close feeder gates as needed. During spring runoff, when creeks flow heavy, fewer feeders needed, gates partially closed. During late summer, when flow diminishes, all feeders opened fully, barely maintaining sufficient volume. The system is balanced at the edge, just enough water, not too much, not too little. This requires constant attention, daily monitoring, adjustments. The operators become experts in water management, learn the seasonal patterns, know which feeders produce reliably, which vary, how to compensate. The knowledge is experiential, learned through years of observation, passed to new operators, refined continuously. Loading is an art. The logs must enter the flume correctly, positioned properly, released at the right moment. The loading point is at the top, where the flume begins. A platform extends over the flume. Logs are rolled onto this platform, one at a time, positioned parallel to the flume direction, aligned carefully. When ready, the log is released, drops into the flume, splashes into the water, immediately begins moving, caught by the current, pulled downhill. The release timing matters. Release logs too close together and they catch up. Collide. Jam. Too far apart and capacity is wasted. Could be moving more logs. The optimal spacing is about 20 to 30 feet. Gives log separation, allows independent movement, prevents collisions, maximizes throughput. The loader develops rhythm, releases a log, counts slowly, releases another. Repeat, hour after hour. The rhythm matches the physics, matches the flow rate, matches the terminal velocity. Everything synchronizes naturally. The loader is part of the system. Human and physics working together, optimizing transport, jams still occur despite best efforts. A log catches on a splinter, on a protruding nail, on a slight irregularity in the flume. Stops moving. The next log catches up, piles against it. The next log arrives, piles on. Within minutes, dozens of logs accumulate. The water backs up, rises, eventually floods over the sides. The flow downstream stops. Logs already in transit slow down. Stop. The entire system jams. This must be cleared immediately. Jam crews are stationed at intervals, every 5 miles or so. They watch for problems, listen for changes in sound. Rushing water suddenly quiet means a jam upstream. They run toward it, arrive at the blockage, assess the situation, identify the key log, the one holding everything. Usually it's the first one, the one that stopped initially. They use PVs, long poles with hooks, reach in, hook the key log, pull, pry, twist, try to free it. If successful, it releases. Begins moving, carries the others with it. The jam clears, flow resumes, everything returns to normal. If unsuccessful, they must break the jam manually. Remove logs one by one, clear space, create flow. Eventually reach the key log, remove it. Then reload all the removed logs. Send them down individually. This takes hours, costs money, reduces throughput. This is why maintenance is critical, why inspection is constant. Prevent jams before they start. Keep the flume smooth, no splinters, no protrusions, nothing to catch logs. The terminal is where logs exit. The flume levels out. Grade approaches zero. Logs decelerate, slow down, eventually stop, float in a large pond. A log boom. Similar to river booms but fed by the flume. The logs accumulate here, hundreds at a time. Workers using PVs guide them, sort them, create rafts, bundle logs together, 20 to 50 logs per raft. Chains hold them, connect them. The rafts get towed to the sawmill. Short distance, quarter mile, half mile. Teams of horses pull them, or they float down final sections of canal. Gravity again, just slower, controlled. The sawmill processes them, cuts them into lumber, boards, beams, products. The lumber then ships by rail, or wagon, to markets, to customers. The flume is the first step, the critical step. Gets logs from forest to mill. Without the flume, none of this happens. The timber stays in the forest, inaccessible, worthless. The flume makes it valuable, makes the entire industry possible. The operational lifetime is impressive. The Kings River flume operated for 33 years, 1890 to 1923. 33 years of continuous operation, 6 months per year. That's roughly 200 operating months. Times 30 days per month, 6,000 operating days. Times 10 hours of active log running per day, 60,000 hours of operation. Times 40 logs per hour, 2.4 million logs transported total, each averaging 2,000 pounds, 4.8 billion pounds of timber, 2.4 million tons, moved by water and gravity, no fuel burned, no engines maintained, just flowing water, just physics. The maintenance costs over 33 years probably totaled $50,000. That's $1,600,000 modern. For 2.4 million tons of transport, that's 67 cents per ton in modern dollars. Spectacularly cheap, unbeatable by any other method. The flume delivered exactly what it promised. Economical timber transport. Reliable, efficient, effective. Until the timber ran out, then the flume closed. Not because it failed, because it succeeded completely. Moved everything. Emptied the forest. No more logs to transport. Mission accomplished. Other flumes matched or exceeded these achievements. The Fresno Flume and Irrigation Company flume ran 65 miles, 1891 to 1914, 23 years of operation. The Sierra Flume and Lumber Company operated multiple flumes, totaling over 100 miles combined, 1875 to 1905, 30 years across all routes. The North Fork King River Flume ran 54 miles, 1896 to 1917, 21 years. Each flume represented millions of dollars of timber transported. Each demonstrated the physics worked reliably, worked efficiently. The technology spread. California, Oregon, and Washington, Idaho, Montana. Anywhere mountains had timber and rivers had water, flumes appeared. The design standardized, V-shaped, 90 degrees, 18-inch bottom, specific dimensions, proven physics. Builders copied what worked. Why innovate when the solution is perfect? The physics doesn't change. Gravity doesn't change. Water properties don't change. The optimal design is universal. Apply it universally. Succeed universally. The forces involved are substantial. A 50-foot log weighing 2,000 pounds traveling at 30 miles per hour carries kinetic energy of 1.08 million foot-pounds. That's the energy of motion. If that log hits something, a jam, a broken section, another log, that energy must dissipate, convert to other forms: heat, sound, deformation, breaking wood. This is why jams are dangerous. Why broken flume sections cause catastrophic damage. The energy must go somewhere. If logs pile up, 10 logs, 20 logs, more, the accumulated energy is enormous. 10 logs at 30 miles per hour represent 10.8 million foot-pounds. When that releases suddenly, when the jam breaks, logs accelerate uncontrollably, fly through the air, smash everything. The physics are unforgiving. The forces are massive. The flume designers understand this. Build accordingly. Over-engineer critical sections. Use heavier timbers, more supports, more reinforcement. Prevent catastrophic failures. Let's examine the forces in detail. Start with a single log, 50 feet long, 12 inches diameter, Douglas fir. The wood density is 32 pounds per cubic foot. The log's volume is pi times radius squared times length. That's 3.14 times 0.5 feet squared times 50 feet equals 39.25 cubic feet. Times 32 pounds per cubic foot equals 1,256 pounds. Call it 1,300 pounds for a typical log. This log sits in the V-shaped flume. Water depth is 9 inches at the center. The log is partially submerged, approximately half its diameter. The submerged volume is roughly half the total volume, about 20 cubic feet. This volume displaces water weighing about 1,248 pounds. 62.4 pounds per cubic foot. The buoyant force equals the weight of displaced water, 1,248 pounds upward. The log's weight pulls down with 1,300 pounds. Net force downward, 52 pounds. The log settles slightly deeper, displaces a bit more water, reaches equilibrium, floats at neutral buoyancy. This is the natural state. The log floats, ready to move. Now gravity acts. The flume slopes downward at 2%. That's a 1.15 degree angle. The component of the log's weight acting parallel to the slope, pulling it downhill, equals weight times sine of angle. 1,300 pounds times sine of 1.15 degrees equals 26 pounds of force. This force acts continuously, constantly accelerating the log, but resistance opposes it. Water drag. Friction against the flume sides. Friction against the bottom if the log touches. The drag force depends on velocity, proportional to velocity squared for turbulent flow. As the log accelerates, drag increases. At some velocity, drag equals the downhill gravitational component. Net force becomes zero. No more acceleration. The log maintains constant velocity. This is terminal velocity. For this log on this slope with this water depth, terminal velocity is approximately 8 to 10 feet per second, 5 to 7 miles per hour. Steady, sustainable, controllable. Increase the slope to 5%. That's 2.86 degrees. The downhill force component becomes 65 pounds. Terminal velocity increases to 15 to 18 feet per second, 10 to 12 miles per hour. Increase slope to 10%. That's 5.71 degrees. Downhill force, 129 pounds. Terminal velocity, 25 to 30 feet per second, 17 to 20 miles per hour. The relationship is clear. Steeper slope equals more force equals higher terminal velocity. The flume designers control velocity through slope. Gentle slopes for safe transport. Steep slopes for rapid descent where appropriate. The physics scales predictably, calculably, reliably. Now consider a turn. The log travels at 20 miles per hour, 29 feet per second. The turn has a 100-foot radius. The log must change direction. Follow the curve. This requires centripetal force, the force pointing toward the center of the curve. The required force equals mass times velocity squared divided by radius. The log's mass is 1,300 pounds divided by 32 feet per second squared. That's 40.6 slugs. Velocity is 29 feet per second. Radius is 100 feet. Centripetal force equals 40.6 times 29 squared divided by 100 equals 342 pounds. This force must come from somewhere. It comes from the flume wall, the outer wall of the turn. The log presses against it. The wall pushes back, provides the 342 pounds of centripetal force, redirects the log around the curve. But 342 pounds pressing continuously against wooden boards is substantial, can cause damage, can break through. The solution is banking. Banking changes the geometry. Instead of the wall being vertical, it angles inward, creates an incline. The log presses against this angled surface. The normal force, perpendicular to the surface, has two components. One horizontal, pointing toward the curve's center. This is the centripetal force. One vertical, pointing upward. This supports some of the log's weight. The horizontal component equals normal force times sine of banking angle. The vertical component equals normal force times cosine of banking angle. For optimal banking, these components should balance forces perfectly. The horizontal component should equal required centripetal force. The vertical component should equal the log's weight minus buoyant force. The banking angle that achieves this equals arctangent of velocity squared divided by radius times gravitational acceleration. For 29 feet per second and 100-foot radius, that's arctangent of 0.26 equals 14.6 degrees, round to 15 degrees. This is why flume curves are banked at 15 to 20 degrees. The mathematics demands it, the physics requires it, empirical testing confirmed it. The builders discovered the correct angle through trial and error. Modern calculations prove they were right. Temperature effects are more subtle but significant. Water viscosity changes with temperature. At 32 degrees Fahrenheit, just above freezing, water viscosity is 1.79 centipoise. At 68 degrees Fahrenheit room temperature, viscosity drops to 1.00 centipoise, nearly half. Lower viscosity means less drag. Logs move more easily, reach higher velocities at the same slope. In winter operations, flumes must compensate. Steeper grades, more water flow, higher volumes. In summer, less steep grades work fine. The viscosity difference is substantial enough to matter. Flume operators learn this. Adjust operations seasonally, cut different logs in different seasons. Send larger logs in summer when flow is easier. Save smaller logs for winter when conditions are harder. Optimize continuously. Adapt to physics. Work with nature rather than against it. Water volume calculations are precise. The V-shaped flume is 18 inches wide at the bottom, 36 inches at the top, 18 inches deep. The water fills to 9 inches depth. The cross-sectional area of water is a triangle. Base equals the width at 9 inches depth. For a 90-degree V, if the depth is 9 inches, the width at that level is 18 inches. The area is 1/2 times base times height. 1/2 times 1.5 feet times 0.75 feet equals 0.56 square feet. This is the area of water in cross-section. The water flows at 5 feet per second. Flow rate equals area times velocity. 0.56 square feet times 5 feet per second equals 2.8 cubic feet per second. That's 126 gallons per minute. For a 62-mile flume, maintaining this flow rate requires constant replenishment. The water exits the bottom at the same rate it enters the top, minus evaporation and leakage. Over 62 miles, losses accumulate, maybe 10% total. So input must be 140 gallons per minute to maintain 126 at the end. This is supplied by multiple feeder streams, each contributing 20 to 30 gallons per minute, 5 to 7 feeders total along the 62 miles. Strategically placed, calculated, engineered, the power output of the system is remarkable. Power equals force times velocity. A log weighing 1,300 pounds moving at 10 feet per second represents 13,000 foot-pounds per second of power. Divide by 550 to convert to horsepower. That's 23.6 horsepower. One log, moving continuously. A flume moving 40 logs per hour averages 0.67 logs per minute. Continuous power output of about 23.6 horsepower. Maintained for 12 hours per day. During peak season, for 6 months. The cumulative energy moved is staggering. This energy comes from gravitational potential energy. The elevation difference between top and bottom. A 1,300-pound log dropping 4,200 feet releases 5.46 million foot-pounds of potential energy. Converts to kinetic energy, heat, work done against friction. All derived from gravity, free energy, unlimited, renewable. The sun evaporates water from the ocean. Wind carries it to mountains. It falls as rain, flows downhill. We capture it temporarily, use it, return it to its journey. Net energy cost, 0. Net environmental impact, minimal. The logs would need moving anyway. The water would flow anyway. We just combine them efficiently. This is sustainable engineering before the concept existed. Before anyone talked about sustainability, the flume builders did it naturally because it worked, because it made economic sense, because the physics aligned perfectly with their needs. Temperature affects the physics. Cold water is denser than warm water, flows differently, has different viscosity. In winter, water temperature might drop to just above freezing, 33 to 40 degrees Fahrenheit. The denser water flows more slowly, requires steeper grades to maintain velocity. In summer, water temperature rises, 60 to 70 degrees, less dense, flows more easily, requires less steep grades. The flume designers account for this. Design for worst-case conditions. Winter operation. If the flume works in cold water, it works in warm water. The reverse isn't true. Some flumes operate year-round, others only in warmer months, spring through fall. Winter operation risks ice formation. Ice blocks feeders, reduces flow, can damage the flume. Most operations shut down when temperatures drop below freezing consistently. The water source matters. Spring water is ideal. Constant temperature year-round. Reliable flow. Doesn't vary with weather, but springs rarely provide enough volume. Most flumes use stream water, diverted from creeks. Small rivers, this water varies. High flow during spring runoff, low flow during summer drought. The flume design must accommodate variation. During high flow, excess water bypasses the flume, returns to the stream, prevents overflow. During low flow, the entire stream might divert into the flume, just barely sufficient. During extreme drought, operations cease. Not enough water. Logs won't move. The system becomes inoperable. Water is the constraint, always. Without sufficient flow, the physics don't work. The system fails. This is why flumes are built in regions with reliable water, mountains with snowpack, areas with consistent rainfall. Dry regions can't support flumes. The physics requires water, lots of it. The terminal velocity of logs varies with length and diameter. A short, thick log has more mass per length, more inertia, accelerates more slowly, reaches lower terminal velocity. A long, thin log has less mass per length, less inertia, accelerates quickly, reaches higher terminal velocity. The flume must handle the range. Short logs moving slowly, long logs moving fast. The design accommodates both. Turns are banked for the fastest logs. The most dangerous scenario. If fast logs navigate safely, slow logs certainly do. The water depth is set for the heaviest logs, the most buoyancy needed. If heavy logs float, light logs definitely do. The system designs for extremes, covers the range, works for all logs within specifications. This is good engineering. Don't design for average, design for the edges, the extremes. Then everything in between works automatically. The cost efficiency is remarkable. Building a flume costs approximately $300 per mile in $1890. That's $9,600 modern. The Kings River 62-mile flume cost roughly $18,600 total. That's $595,200 modern. Building 62 miles of railroad would cost approximately $248,000 in $1890. That's $7,936,000 modern. The flume is 7% of the cost. Operating cost is even more favorable. Flumes require no fuel, no coal, no wood, no hay for horses, just water, which is free. Maintenance costs are minimal. Repair crews, replacement boards, grease, maybe $1,000 per year. That's $32,000 modern. The flume is nearly free to operate. The physics do all the work. This is why flumes proliferated, because they're economical. Moving timber for pennies per 1,000 board feet. The efficiency is mathematical. Moving 1,000 board feet of lumber, approximately 5 logs, 1 mile down the flume requires about 15 minutes of flow time. The water used is roughly 1,000 gallons. That water flows down the mountain regardless. The flume just captures it, channels it, uses it temporarily, returns it to the stream at the bottom. Net water consumption, 0. Energy input, 0. Just gravity. The only cost is initial construction. After that, the system is essentially free. This is physics perfected. Maximum efficiency, minimum input. Nature doing the work. Modern physics confirms what the flume builders knew empirically. The Navier-Stokes equations describe fluid flow. They model water flow in the V-shaped channel, predict velocity profiles, turbulence patterns. The empirical designs match theoretical predictions. The 90-degree V angle is optimal. The water depth ratios are correct. The banking angles on curves are precise. The 1800s engineers got it right. Without computers, without formal training in many cases, just observation, experimentation, intuition. The legacy is mostly forgotten. A few flumes survive as historical sites. The original flumes are gone, dismantled, salvaged, left to rot. The physics live on. Every time water flows downhill, every time something floats, every time gravity does work. The principles the flume builders used are eternal. They discovered practical applications, created working systems, moved mountains of timber. I'm using nothing but water and gravity, the simplest forces, the most elegant solutions. The log flumes were physics made practical, engineering made simple, nature harnessed efficiently. They worked perfectly for exactly as long as they were needed.